Hey everyone, thanks for having us on. Today we'll be talking about hacking CI/CD systems. First things first though, we'll do a little introduction, and then we'll quickly go over what we'll be talking about today, in case you're on the fence about actually watching this talk. I'm Echo, or James. I work as a backend engineer, which is the fancy way of saying I stare really hard at computers and encourage them to do better. I'm an internet mole goth and have been hacking since the mid-90s, which I think makes me a senior citizen in the bug bounty space.
Hi, I'm Sean. I'm a startup engineer at AssetNote. That means I do everything at the startup from management to backend to middle end, not the front end. I do DevOps, I do product management, and the general firefighting. These days, I frequently spend my time automating bug bounty techniques, and then I just leave them until they break forever. Otherwise, I just doom scroll Twitter. Yeah. So today we'll be serving you 5 courses of CI/CD exploits and adventures. We'll be mostly covering the following topics. As an introduction, we'll be covering who is CI/CD.
Some hacker bedtime stories.
We'll be going through some CI/CD blue team horror stories.
How we own some CI systems and how you can own some CI systems.
And finally, what you can do to stop people like us owning your CI system.
All right, DevOps Thought Leadership Image Party, let's go.
So if you're familiar with software development at scale, you should be familiar with DevOps. And if you do a DevOps good, you'll be using CI/CD and the supporting systems to automate testing and deployment of your code as changes are approved. But business excellence aside, CI is where you push code. That's the continuous integration. And then they run a set of tests and scripts against your code. And continuous deployment, or CD, is where they deploy the code straight to production. I mean, not always to production, but you get the idea. This landscape has a heap of providers, and you may be familiar with them already. Some of them include Jenkins, GitHub Actions, and even GitLab's Runner or CI.
There's a ton of existing literature covering this area, so we won't tell you how to do DevOps well. Just know that all 10 times full stack developers love this stuff and trust these platforms more than you've ever trusted anything in your life. That background is fairly important when looking at CI systems.
And on that note, why should you care?
So yeah, CI and CD jobs have some pretty spicy secrets usually. When we talk about hacking CI/CD systems, we're actually talking about a few main areas of attack surface. In CI/CD, context is even more important than ever because there's a high degree of freedom given to users which would constitute security flaws on irregular applications. Examples of this would be RCC or SSRF, RCE or SSRF, which are features rather than bugs when you talk about CI/CD jobs. So in order to hack CI/CD systems, you're looking to escalate your privileges so you can change your scope and then see what you can shake out from your new vantage point. Some examples of ways we've commonly been able to do this are information disclosures in the build context. CI/CD jobs require an eye-watering number of secrets to download, configure, build, and deploy software projects in an automated way. Sometimes you can leak these secrets from the orchestration platform. You also need access to other systems. Automation basically requires access to other systems in order to be able to automate things. So CI/CD jobs often have broader access, sometimes inside of the build context, sometimes outside of the build context. So pivoting from the build runner to another system can be a valid strategy for getting loot. You also often have access to other people's code. Given the cost of running cloud infrastructure, especially on free or cheaper tiers, CI runners will handle jobs from multiple different users. These users can be projects under the same organization or users with no organizational relationship with each other. Gaining access to secrets or code from other users is a huge win. Escape and persistence is another vector. The security context of the CI/CD job running on the runner server is often heavily constrained to make sure users can use the CI/CD system, or as we prefer to call it, RCE and SSRF as a service, without compromising or accessing anything sensitive. Again, given the cost of the underlying infrastructure, which is usually on AWS, GCP, or Azure, there are resource limitations placed on the runners too to present excessive network, compute, and storage usage, and especially to limit abuse like cryptocurrency mining, network transfers in bulk, and network scanning, that kind of thing. Rendering these controls ineffective can lead to extended or unlimited access to resources which a bad actor can use to do bad actor things. This has a real financial impact to the company running the CI/CD infrastructure. Circumventing scoping and controls to expose more secrets is another one. This includes escaping sandboxes such as containers, escalating your privileges, potentially gaining access to secrets normal users should never see, which can in turn be used to further exploit the CI/CD system via any of the methods we've just discussed from a changed security context. Okay, let's discuss how you can approach a CI/CD system to assess these vectors. After that, we'll dig into the good stuff by discussing the attack vectors we've seen with some choice examples to show you what we mean.
So when approaching a CI system, there's a few key questions you should ask about the platform and the features that it advertises. The first is, how are they getting my code? For a CI/CD system to be useful, it needs to be able to get user code and run some kind of testing or transformation on it in order to fulfill its purpose. It needs to do that frequently without use or intervention, and that means secrets, like machine secrets. Which secrets did you have to give it for it in order to work? How likely is it that other people have provided the same secrets? So while poking around inside a running CI job, you should go hunting for those secrets and see how they're stored and see if you can access other people's data or access secrets for other users. The next question you can ask is, how are they running and building my tests? And can I control this? When it comes to CI jobs, there's usually a level of customization available as to what's actually run inside the test or build job. In our experience, there's often a very small amount of sanitization done, mainly to give users more flexibility. Play around with the build scripts, test various commands and configurations to see if you can inject shell escapes or append additional commands. They may be running these outside of the context of where you're building, or when the build agent passes them incorrectly, throw you into a completely different. Where they are running my code, then you can ask what else is hosted there. Similar to the previous point, if you can find out where the code is being stored and you poke around inside the build job, you might find configuration or code for other users' in-flight jobs. Timing might be a valid vector here. They might be using containers alongside you or processes within the same container to do the same. Next, you can ask questions about the artifacts. And a common use case for CI/CD is storing the built software packages or the results of tests as artifacts. So afterwards, users can view them or review them. These are normally stored and persisted elsewhere for access via the CI/CD system or via front-end web UI. Similar to other file upload vulnerabilities, controlling the name, the content, can often lead to controlling what is essentially untrusted input into the CI/CD platform, or to the web application, or to the web UI. Here's an opportunity to look for things like XSS, path traversal, and file inclusion bug. The next question you can ask is a bit more about the operating system itself. What does our operating environment look like? What can this tell you about the infrastructure? This one can be a lot of fun because even if you don't escalate privileges or escape confinement, you're guaranteed limitless callbacks on your reverse shells, and you get some real opportunity for hacker LARPing here. Interpreter sessions can open, but seriously, this can lead to some really good bugs, as most CI/CD jobs are running some kind of jail or truth. And contrary to good container security advice, people just use containers as a security boundary, even when they really shouldn't. This can lead to disclosing some very juicy secrets, such as the CI platform's cloud credentials, metadata endpoint, and you get the picture, anything cloud native that's really our sandbox. Because in some cases, you'll find yourself operating in the same security context as the platform. So, with this high-level methodology in mind, let's dive into some of these vulnerability classes and actual bugs we've found to demonstrate some of these.
All right. Let's say you've found a CI pipeline you're interested in. Drop a reverse shell into the build process, put your black hoodie on, dim the lights. And now you start staring at a shell on someone's infrastructure. What do? One of your first goals when you start auditing a CI system is to disclose as much information as possible. Some of the first things we try doing are digging through things like accessible files. We've got some examples in the slides here of just like really quick win commands we use. What kind of environment variables, both the process that you are running your job as and other processes on the system might have access to. Any open network connections within the actual CI environment can be really telling as to what kind of external systems you might be able to access using some of those secrets. And the process tree, like how is the build being called? What are the parent processes to the actual build job itself? Can you interact with those things?
So in our case, we were able to obtain the build agent source code for the build system due to improper directory permission. This meant we knew exactly how our builds were being run and how the inputs into the web app side of the CI system mapped to inputs in the various build stages, including those running at a higher privilege level. We were able to use this source code to find two interesting bugs related to information disclosure. Now, this isn't always possible if the build agent is written in a compiled language, unless you want to go into binary reversing. But in our case, it was a mix of Bash and Python, which is pretty common and makes our life a lot
heaps easier. All right. Auditing the code showed that the build path was not being sanitized and was being executed inside of a shell. So when the job was actually being run, the path in which the job was being run as the current working directory was a user controllable input. I'm sure there's a number of like really valid reasons that you would want to do this for certain build systems. And like this is a good reminder that flexibility in these systems is really common because the requirements of different developers are actually quite broad. We attempted typical stuff like shell injection because we could see this was controlled. This phase of the build was being run before a sudo into a constrained build user. So it actually was like quite a tantalizing input to try and control. That step switched the user context to the build user, which was like heavily restricted. It couldn't sudo, like file permission restrictions, etc. If we could inject code here, we'd have access to the service account of the CI runner, which had way more privilege. Unfortunately, the path was being validated for special characters. Fortunately, it was only client-side validation, and a quick burp session showed that we could actually inject the special characters just via repeater. Once the new path was accepted, we found another issue in that the path was being checked to ensure it existed before running the job. This didn't seem like a deliberate security measure, but rather a happy accident from a security perspective. Thankfully, ext4 is very resilient in a featureful file system and allowed us to create all of the folders and files, including the special characters needed for the shell injection. So the path check passed and we were able to run with our modified injected path.
Using this trick, we were able to dump the environment of the CI runner, which included the GitHub private keys and a bunch of other tokens. Upon validating these keys, we found that they gave us access to the repos of every customer using this CI platform, not just our own. At the time we found the bug, That was around 50 or 60,000 users, various GitHub repos.
Nice.
Phenomenal.
So in this example, we learned some key ways you can leverage CI systems to access sensitive data and gain RCE outside of the build context. For attackers, this is a reminder to always test all of the inputs and always check to see if validation is only present on the client side. Also, continually test your assumptions. We might have stopped when we saw that the file path was being checked, but instead we tried to create a path that would satisfy the check. And we were able, due to Linux's relaxed file naming rules, which I think a lot of people might have assumed might not have been so relaxed as they were.
For defenders, there's a few key lessons here. Firstly, you should always sanitize your input, preferably on the server side with your UI feedback, instead of relying on just client-side validation. You have to treat all user input as untrustworthy. Also, making sure that you scope your tokens very aggressively down to be only given the minimal privilege necessary for what the user needs. The last thing you want is one bug to leak the tokens for all your users. The next part is around how you orchestrate your build. And often we'd recommend trying to segregate the build orchestration software or the code that lets you run the user code from the user job itself. But we understand that's not always possible. So in addition to that, we recommend heavily locking down the permissions and the container permissions to prevent access to this code. We found that after we reported this bug, they decided to change the user permissions on all of the runtime or all on the job running code, so we couldn't check it anymore. This effectively meant we couldn't audit any more source, and as such, we can't find any more bugs with it, unless we just start black box brute forcing.
In contemporary cloud computing, it's more and more common to see layering of cloud services to build systems generally. In the case of this CI system, the underpinning orchestration and compute service was actually provided by Azure DevOps pipelines. We found this out when we found, going back to the point about looking to see what you have access to and trying to find source code of like build agents and things like that. We actually found a rendered Azure Pipelines YAML file. It's an artifact on the build file system, just lying around. Something we also should not have had access to, really. There was no real reason for it to be there on the file system and accessible by the build system. But we did, so we audited it. It was clear it had been rendered from a template by the web app and build scripts, so we started reading the documentation for Azure DevOps pipelines. We noticed a really useful feature here for developers, and as it turns out, also for attackers, which allowed substitution variables to be injected using string interpolation via a very rudimentary kind of templating syntax. We, of course, tried to use that to launch a shell. And that worked. These commands were being run well before the build agent actually even ran. We were running as the same user in the same security context as the entire build system. We were immediately able to access the Azure DevOps service user. As it turns out, it had passwordless sudo, so we had root access to the host container, which was pretty exciting.
So with access to the host container as root, we started looking around for ways to escalate even further. We found the number one container escape crime, which is an exposed Docker socket under run Docker. We created a super privileged container, which meant a privileged container, but we also used the root network namespace and bind mounted the host proc and file system into that container. We chose Ubuntu as it's got a fairly complete Docker image and it's easy for us to install additional. What this meant was that we now had effectively access to the host machine running this container. From the host system, we were able to then bypass the firewall rules, which had been applied to the build containers via IP tables, and as such, access the metadata IP of our cloud provider. We then managed to use this to pivot further into the platform's cloud environment. And needless to say, we had a pretty big payday on this. We were able to take this even further eventually. But in the interest of time, we'll stop here because we've already made our point.
As a counterexample, a different CI provider entirely, we were able to gain access to the builds, which is nothing special. But we did find a very similar container escape. This time there was no Docker socket available, but via an abuse of cgroupfs, which is a kernel mechanism for controlling, monitoring, managing various system metrics available to namespaces and subprocessors, the host machine was able to be accessed. However, this machine had been provisioned dynamically for the job, so the job was siloed to this machine, and the machine was destroyed once the job was complete. So there was no possibility of grabbing other user secrets or artifacts or anything. Additionally, all of the orchestration software was running on another host entirely, so we're not able to gather further detail or escalate our privileges by accessing stored secrets or anything like that, as there weren't any on the system. The cloud metadata IP was made accessible by removing the firewall rules preventing access once the host machine was accessible. But the tokens were so heavily scoped that no secrets were revealed. In essence, whilst a cool hack was done, the impact was basically zero given the security impact had been effectively mitigated by all of these controls that had been put in place. It's very important to consider this when reporting bugs like this. In this case, it was not worth reporting as it was marked informational and, for good reason, really. Like, this was an example of essentially doing this well and doing it correctly to make sure that, even if someone does leverage the build system to do unusual things, they don't actually have access to anything sensitive.
So we've seen a few good examples of the kind of loot you can find on CI systems. If you approach it methodically, you test your assumptions, and you sort of build a general understanding of how the platform is laid, and ultimately figuring out when, where, and how your builds are run. We've seen some of the pitfalls that exist for people building CI systems and how they've led to huge paydays for attackers. In our case, for bug bounties. But how do you do it right? And how do defenders build a more robust platform? As we said before, you shouldn't trust user input. Understand how the tools and platforms and frameworks that you're using to transform user input and how they work before, and make sure you validate all the inputs that go in. As Mulder would say, trust no one. Second point is use ephemeral VMs. The less you have lying around between builds, the less likely you are to get caught and breached. Now, this is distinct from using containers, which we might seem are similar to VMs, but distinctly the isolation of a VM provides a substantial amount more of security. Next, we should use network policies or firewall rules to prevent access to resources which aren't needed by the build process. Typically, anything in a private CIDR range should be blocked during the build, especially for the CI job. We recommend implementing least privilege principles when running CI jobs. Do your users really need to install arbitrary packages? Probably. Do they need the Docker socket? Probably not. Do they need to be able to access the source code of the orchestration software? Most definitely not. We recommend avoiding to run jobs or orchestration software as root. User namespace separation is often a good solution here if you can't separate the orchestration software onto a totally separate system. If you're running a container as privileged and expect it to provide any kind of security boundary, you should drop that assumption right now. A privileged container is functionally equivalent to root access to the host in most cases. If not now, wait a month until there's a new vulnerability, then typically only impact privileged containers later. Don't mount the Docker socket inside a container. There's no good reason to do it. Also, if you expose Docker on the network, enable TLS and don't mount the certificates in the container. We have also seen this. Also assume that people will either mine crypto on your runners or use them to run mass scans. You should appropriately limit and restrict the resources that your VMs or your containers have access to. So thank you for coming to watch our talk, and hopefully this has been insightful into how CI systems are horribly vulnerable.
And thanks to everyone for organizing NarmCon, and thanks for having us on.